We're back, and everything is ready for us to start exploring delta method. So again, delta method allows us to estimate the variance of nonlinear functions of regression parameters. The reason I'm saying regression parameters is because once we run the regression, usually, whether it's ordinary least squares or maximum likelihood, usually we are able to obtain not only the parameters themselves, but also variance covariance matrix of those parameters. And we fitted ARMA model to time series, and that model produces variance covariance matrix of its parameters. So to motivate the method, we will start with univariate example. It's just easier to sort of see how the math works, and then we'll apply it to multivariate. So multivariate meaning combination of parameters, but with univariate we have just one parameter and then some sort of a nonlinear function on the parameter. So let's see. We will start with the following. We will apply the Taylor expansion to that function. So suppose you have a function of a parameter, and we'll see where this is applicable to what we use in practice, right? So we will apply it to a function of parameters, but we will apply it around the mean of its argument. Now, what's important when we're applying Taylor function is to understand this is not around the mean of the function. This is around the mean of its argument, function argument. So if we do that, we have a usual Taylor expansion, Taylor series expansion. Let's just look at the first order. So we're not looking at quadratic terms and so on. First order, very simple, right? So it's a discrepancy or deviation from the mean multiplied by derivative around the mean plus function value around the mean. So now if we apply the variance operator to the function on the left hand side, we will get this expression on the right hand side. So I'm not going to derive it, but it's very simple actually, because think of this. If we're applying the variance to the function f, and then we're applying it, which is approximately equal to the variance of the right hand side. So think of this. This first parameter value of the function around its mean, it's a constant. So when we apply the variance, we can just exclude it because it's a constant. When we're applying constants can be removed. So we need only the right hand side. But on the right hand side, the derivatives is also estimated at the mean. So this is a constant too. But we're multiplying constant by the varying expression. So if we're getting the variance of this expression, there is a simple rule. In statistics, we know is equal to square of the constant. So it's a square of the derivative multiplied by the variance of this expression. But the variance of this expression is simply the variance of x, because x mean x is a constant itself. So it's a very simple derivation, but basically what we're saying is the variance of this function is approximately equal to the variance of its argument multiplied by the first derivative squared at the mean of the argument. Done, right? So now how, think of this. Suppose we have a function, like when can we use this actually, a univariate case? Think of a function. Suppose you have a function y which is equal a and then exponent alpha t. Now where do you see this? This is any kind of a growth, exponential growth, explosions. If it was physics, it was like a lot of processes in physics like that. But in economics, it's just it's exponential growth, alpha being a growth rate. So, well, how do we solve this? By logging, right? So we get a logarithm of left and right hand side. We're linearizing the problem. So when we linearize it, we get what? Logarithm of y is equal to logarithm of this expression, which is logarithm of the constant, a amplitude, multiplied by alpha t. Exponent goes away when we logarithm it. So it's a linear regression, right? So we on transformed variables. It's a simple linear regression. There is a constant and there is t, which is your parameter, and slope and the intercept. So we can easily estimate the intercept. Great, right? So we can easily estimate intercept, and we can even easily obtain the variance of an intercept. But what is the variance of this amplitude? We don't know that, right? Because we know the variance of the log alpha, but we don't know the variance of amplitude itself. So that is the case where we can try to apply delta method. Because see, what is the amplitude? It's this intercept of this linear equation, right? But exponentiated. So it's basically our estimator of an amplitude is an exponent of an estimator of the intercept of this linearized regression. But we want to know the variance of the amplitude. Again, we know the variance of C, right? And then we know the function. So it seems we can apply delta method, right? Because we know the variance of an argument of a function and we can calculate the derivative. So we can apply delta method here. So we're trying to now estimate variance of this amplitude A based on the variance which we got from the regression of C, right? So how? We apply the delta method, simple, right? We get the variance and multiply by the derivative. So it happens so the derivative on exponent is an exponent itself. So it's basically exponent squared. And we got this simple expression for delta approximation. You can check it yourself if you're interested, right? So that was our simple univariate case, right? So all we needed was a derivative. We square it and multiply by the variance of an argument. It seems very simple, right? So if we translate this to our case, in our case we have a multivariate or bivariate case, right, where we have this function has two arguments. It has a constant and phi, right, in our ARMA model. Again, going back, we're trying to calculate this this expression, long run mean, and for that we need the constant and phi. So it's a function of two variables. Well, having function of two variables of this form, we now need to use a multivariate form of Taylor expansion, right? I'm not going to be deriving it again. It's standard statistics, but it's very easy to be done, and you will see how similar to univariate case it is if we are using vector notation, which again I teach in my refresher class. So if we translate this into a multivariate case, right, we will take these two parameters c and phi and put them in a vector. So we will represent them with a vector c and phi. It's a vector with two elements, right? We will call this vector x in this case. Okay, we got this vector, a column vector in this case I want, right? So my Taylor expansion will look like this, right? So this nabla is a gradient operator. So the gradient operator is a vector. You take this function f and then take the derivative, partial derivative, with respect to each of the elements of this x, vector. And we have two elements, so this gradient will be a column vector of two derivatives, partial derivatives. That's all, right? But now, how do we apply the variance to it? The only twist, right, the difference with the univariate case here is the following. We cannot square the gradient because it's a vector. We cannot just square it like as any other vector. But I teach it in my refresher that we instead of this expression, square of the derivative, we get a quadratic form. It's a similar expression, but it looks like this. What is the quadratic form? So instead of squaring the gradient, which we don't know how, right, because it's a vector, we take the variance of my arguments, but my argument is a vector itself. So what is the analog of the variance of a vector? It's a variance covariance matrix. I notice like this, right? Our ARMA estimation will produce this matrix actually, a variance covariance matrix, 2 by 2 matrix. And then we'll create a quadratic form by multiplying it from the left and from the right hand side by the gradient, which is a vector. We know how to multiply a vector by a matrix, so we do that, right? Dot products. So this is an analog of a square of the derivative. So instead of having a square in the scalar case, in the vector case, we have quadratic form. We multiply by this vector from right and from the left, with not forgetting to transpose the matrix, right? So because on the left hand side you need to have a row vector, and on the right hand side you need to have a column vector. So that's what's going on. It's very simple, right? You calculate the gradient. Once you're done, you have the you can multiply this variance covariance matrix like that. So I'm going to show you how to derive the expression here. So this expression, by the way, is a scalar. We are using matrices and vectors, but the result is a scalar, just one number. It's not multidimensional. Okay. So I'm going to use the SIMPy package to derive the expression, the closed form expression for here. SIMPy is symbolic computation in, or like what's called computer algebra in Python. Very useful package. So I'm going to use SIMPy to do what? To calculate the gradient. So what is the gradient of this function? I have this function. I need the derivatives with respect to first argument, which is constant, and then the second argument. And unsurprisingly, the gradient looks like this, right? Why? Because when we take the derivatives with respect to constant, this goes away, and then we have 1 divided by 1 minus phi. And we got it here, and then once we get the derivative with respect to phi, it's going to be the constant remains there, and 1 minus phi squared, okay? There's a minus sign, if you remember, but it negated by this minus before the phi. Anyhow, this is the gradient. So actually, from here, we could just go straight and calculate this expression, right? Because we needed the gradient, we have it, and we have variance covariance matrix. We can just multiply and get it, right? So, and I'm doing that actually in this piece of code. Let me show you this piece of code, right? So I calculate the gradient. So because the gradients looks like this, it's very easy to calculate. I have phi and I have c's, right? So I calculate gradient. I set it here, right? And then I have variance covariance matrix, the output parameters of my regression fit. And then I multiply it from the right hand side, from the left hand side, and the output is 0.89. But before going here, I just wanted to show you that I'm going to derive the closed form expression for this. How? Using SIMPy package, right? So I'm going to get the gradient, and then I'm going to show you this, right? So I get the gradient multiplied by sigma, but I do it in a symbolic form, not numbers, symbolic form. And I get this kind of an expression. And it's easy to see that, for instance, this element this in the middle is 1 minus phi squared. And the element on the right hand side denominator is 1 minus phi in cubed, and on the left hand side it's 1 minus phi power 4. Why? Because we're multiplying gradient from the left and from the right, so the output must have the denominators as powers of 1 minus phi. So it's either 1 minus phi power 2, 3, or 4. So that's why my final expression is this. So you could actually plug this expression, because you know c, you know phi, you know all these parameters, right? So you could plug these and calculate the final. So here, this is, by the way, covariance of two parameters. So you could use this expression. But as I said, as a matter of fact, I'm not using that. I'm directly numerically calculating my gradient and just multiplying my variance covariance. Now let's get back to our result. So our result is 0.89, right? So this is interesting. Now we know that the variance, dispersion of the estimate 2.31, you know, this dotted line black, we know what is plus minus sigma from it. So the green lines are showing plus this dispersion 0.89 and minus this dispersion. So these are sort of confidence bands, 1 sigma confidence bands. We could do 2 sigma if we were if we wanted, and we see that the 2% inflation rate is well within these confidence bands because there's so much noise. We have a short series, only 49 data points, and they're very noisy. Yes, we got this 2.31 long run inflation, but we're saying the estimator itself has a lot of uncertainty, plus minus 0.9 pretty much. So that's why I'm going to declare that this ARMA model is consistent. Well, ARMA model and estimated long run inflation mean is consistent with Fed's target of 2%. So I'm not like there's so much noise that it's basically whether it's 2.31 or 2%, we cannot really statistically differentiate. So it seems like Feds are doing their jobs, but yeah, there's still a lot of noise. So a lot of people were annoyed actually around this high inflation. So it's actually causing political problems for the current administration in its re-election, because inflation became such a hot subject, and it's again like population doesn't like inflation. American especially, we don't like inflation here. Anyhow, but we see that Feds are trying, right? So the data is consistent with them trying to get the inflation to 2%. Okay, now let's compare this result to bootstrapping. So I said that the delta method is approximation, and bootstrapping sometimes can be a better approach, right?